Today we have quite a treat, and that is a Harvey Mudd institution called Borrelli Coleman. And so they are going to tell us all kind of juicy stories, right? Bob.
Thank you. Well, juicy, I don't know how juicy they will be, but I'll try to tell you a little bit about my background. It's been a long time. We've been here. Let's see, I came in '64, and Courtney came in '59. When I came to Harvey Mudd, there were only 5 people here, 2 geometers, 2 topologists, 1 person in differential equations. And I think that's basically it. When I was hired, I was the token applied mathematician. I finished my PhD at Berkeley in '63, and I went to Berkeley because I thought that they were going to have an applied math program. In '55, they made a bid to bring the Quran Institute en masse to Berkeley. It failed. They only brought 2 people, Bernie Friedman and Vic Tursky. They were the only ones who came to Berkeley. And Bernie was my advisor for a while. And so I went to Berkeley and I started working there. I ended up doing pretty theoretical things, but I really wanted to go into industry. So when I got a degree, I decided that I would work down the peninsula, and I interviewed at a few places. I went to SRI, Stanford Research Institute, and I interviewed there, and the guy asked me, "What is applied mathematics?" So I told him some pretty highfalutin things, and he looked at me and he said, "No, applied mathematics is 17th century mathematics." Well, that was not a good sign, so I didn't consider going to SRI. So I interviewed at Philco Ford in Palo Alto, Sunnyvale, and I was hired there. And my job was they were putting up communication satellites. And if you ever worked at all in celestial mechanics, then you'll notice that when you put a satellite into a circular orbit about the Earth, that if you look at the principal axes of that satellite, the stable position is when the major principal axis is pointing toward the center of the Earth. So that's where they put the antenna, right there on that principal axis that would point toward the center of the Earth. The trouble is that gravity, being a conservative force field, any perturbation at all to the satellite would not be damped out. It would continue to oscillate back and forth forever. So the brilliant people there at Ford Aerospace, or Philco Ford, decided that they would, in the gimbal axes of the satellite, they would put springs and dampers with various spring constants and damper constants. And so they had a large grant from the federal government to actually design the correct values for these spring constants and damper constants. Well, how did they go about doing this? They had a large computer, and they do what a lot of engineers do. They simply went to the computer and tried out various values. And they kept searching, and they kept searching, and searching, and searching until they find something that works. I didn't think that was very nice. So what I did was I found the best possible values for those constants and proved it. And I did it theoretically, wrote a couple of papers. I was very proud of what I'd done in that first year. I took it to my boss. He looked at me and he said, "I'm not interested in this. I don't want to hear this." Why? Because they were charging the federal government for using the machine. I didn't know that. So I was optimizing on the wrong thing. Well, I knew I wasn't long to stay in industry, and I happened to be looking at Time magazine. This was in '64, and I saw an article about Harvey Mudd College there. And so I decided I'd call up and apply. So I did. came down. Courtney wasn't here. Courtney was back in Baltimore on leave. And in fact, you weren't even here to interview me.
No.
Yeah, so I...
Otherwise, it would have been totally different.
Okay. So I came down and went through the whole process. And Bob James, who was the chairman at the time, kept me appraised of how my situation was going and how much, did they have a full FTE or not? And Bob was a very precise person, if you've ever known Bob. Sometimes there was a 3/4 of an FTE available. Sometimes there was a 5/6 of an FTE available. Sometimes there was a 7/8 FTE available. I thought, well, this is too iffy. I probably shouldn't count on this. And to make matters worse, I was interviewed by the president at the time. And he looked at me and he said, Bob, I want you to know that if you decide to come here, I don't know where your salary is going to come from more than 3 months in advance. So with that auspicious beginning, I decided to accept the offer and I came here. Now, Courtney, do you want to say a few words about how you got here?
Well, is this on?
Yeah, I think it's okay.
It's okay.
Is it okay?
Yeah.
When I came back from a year's leave of absence and they'd hired this guy, I knew something was odd. You should have seen his haircut. It looked like a monk's haircut or something. So I asked him, who did that? Well, my wife did it. Why? Well, we had a big cut of income coming to Harvey Mudd from, industry to academia. So we thought we'd economize on everything. I said, don't do that again. Yeah, really odd. Well, I came to Harvey Mudd. I think I was the last hire at Harvey Mudd ever, never to visit the campus and never to be interviewed. I was in the East at the time, and I was interviewed by an engineer who'd just been hired himself. And after that and their experience was seeing what happens when you hire someone that no one has ever seen, they insisted that every person being considered must visit the campus and be interviewed by faculty. So I'm a good example of a bad start. Anyway, how did I get into applied math? By accident. And the accident had to do with graduate school and the way they scheduled the courses. I got my bachelor's degree from Berkeley, and I particularly liked logic and set theory. Thought they were great, absolutely great. So I was convinced I was going into one or the other of those. Got to Princeton. The logic course taught by a very famous logician, Church, was after lunch. Well, like many people, I was sleepy after lunch. And Church, very nice man, but he spoke in a monotone. So I went to sleep. I thought, well, okay, it's not going to be that. Logic is out the window. So what course could I take that would be interesting and I liked? Well, my second choice was algebra. And Artin was the algebraist, really created, in a sense, 20th century modern algebra. Marvelous lecturer. But when he lectured, all problems were solved. There was nothing left to be done in modern algebra. I was a graduate student looking for a thesis. There wasn't going to be any thesis there. So that left differential equations. And by pure chance, the differential equations course was not a course in differential equations. It was a course by a visitor who was working on some problems of his own. So it was a course in a research area in differential equations. So that's how I ended up in differential equations. And let me go back. The most boring course I ever took when I was undergraduate at Berkeley was, guess, differential equations. Anyway, I ended up in differential equations, so here I am.
Who was the visitor?
Pardon?
Who was the visitor?
Stephen Diliberto. I don't know if any of you know him. He was at Berkeley for many years. Oh, one last thing. My thesis advisor was Lefschetz, Solomon Lefschetz. I don't know if any of you have met him. He started out as an engineer. So he was in an industrial accident at Westinghouse, and both arms were burned off from here to his hands. So at the time I knew him, he had wooden hands and a wooden arm. Later he got the aluminum, so they a little lighter. But my wife knows very well what it feels to be clapped on the back by a man with wooden arms. Enough.
Where is it?
This one?
Is that it?
That's 40 years.
Yeah. Okay, what I'm gonna try to do is to tell you the things that Courtney and I have worked on for the last 40 years. And when Alfonso asked us to talk, I started putting these things down, and I'm rather amazed at all the things that we've done. And I'll talk about some of these things as we go along. Some of you know about them already, of course. Others of you may not. And these things up front are the things that Courtney and I have worked on and published. So they're up here. Anyway, first thing we did when we got here, or when I got here in '68, Courtney and I thought it's a doggone shame that there is no course in differential equations in the core. At the time at Harvey Mudd, there was a 3-year mathematics course that everybody took. And the first 2 years was out of the same book called University Mathematics by Bob James and so on. That was pretty boring. Differential equations was just a little piece there. So Courtney and I had an idea that maybe what we ought to do is to try to put spotlight differential equations a little bit and bring it down to the freshman level. So we created something called the Freshman Differential Equations Seminar, and we embedded that in something called the Freshman Division. Now, those of you at Harvey Mudd know that Harvey Mudd's always complained that they're overworked, and we always try to do something about it. Well, we did too when we were here, and what we did was took the freshmen, removed them from the normal course of things. They didn't get grades, and we designed the curriculum in the freshman year so they would only have to work on 3 things at any one time. Differential equations being one of them. It was a very intensive 8-week course. And so, Courtney, can you put up the differential equations one?
Which one is that?
Well, let's see. If you just want to see. Here. Oh, that's all right. This one here. If you want to see what the freshmen at Harvey Mudd suffered through when we were here, this is the table of contents. The people who put this together was me, it was a physicist, and it was an engineer. We did it jointly. So we put this program together. And this was for Harvey Mudd freshmen. And they survived it, and I thought we did fairly well. Unfortunately, the faculty didn't survive. The freshman division lasted exactly 2 years before it died. Why did it die? Because the faculty had to constantly be in communication with one another. If you're going to do something jointly, you've got to be talking to one another all the time. It just got to be too much work. So we couldn't get faculty to join the freshman division, especially young faculty without tenure. So the freshman division died. That was the end of that, and the end of the freshman DE seminar. So we went on from there, and what we decided to do, Courtney and I, was to write a text for the junior year in applied mathematics. Everybody at Harvey Mudd had to take that junior year in applied math. We had a lot of engineers and physicists and chemists, and some mathematicians as well. So Courtney and I started writing, and we kept writing, and writing, and writing. And we ended up with a text that was about 2,200 pages, right? Which you call the monster.
It says it was 2,500. It wasn't. It was only 2,250.
So we use that as a text for about 7 different courses at Harvey Mudd. And students remember that, and they often come back and ask if they can get copies. I'm not going to copy 2,200 pages.
Set of notes, and I remember one year, after the course was over, they had a ritual book burning. I was just glad it wasn't a faculty burning.
Well, what we did was we solved that problem by putting it all online, all 2,200 pages. So it's available here. If you go to Claremont College's digital library, there are 3 items there that Courtney and I worked on. And this last one, mathematical methods, models, and applications for engineers, mathematicians, and scientists. That's it. So it's all available online. The interesting thing about this text was we had a lot of modeling involved, because we thought that modeling should be part of differential equations. Modeling and visualization. Well, we didn't have many computers in those days, but we sure did a lot of modeling. So in our text, at the end of every section, were several models that one could work on. And as we began to do this more and more, we decided that some of the work that the students were doing in these models was so good that it was a shame to just dump it into the wastebasket at the end of the semester. So we created a journal called Interface. And that's this up here. And this journal is an interdisciplinary journal of student research. So we selected the best reports that came out of this course that we were teaching and other places, and we published them. And Interface lasted for, about 20 years? And then it kind of faded out. But it's coming back again. So it's going to be back, and it's going to be online this time. And by the way, Interface is all online here, so you can go to the Claremont College's digital library, and you can browse the items by collection. And here they are. And you can read them all, you can print them, you can do whatever you want. So it's something that we didn't have available back in the old days. That's why we printed all these things. We sent copies to every Harvey Mudd student, to the trustees, and to clinic clients as well. So anyway, that's Interface. And we tried to take care of that part of what we were doing. And then as time went on, about in '73, we looked over at what the engineers were doing. They had something called the Engineering Clinic, which is a program that brings real-world problems onto campus so that students and faculty can work on those problems in a professional way. So I thought that was a really good idea, and I wanted to get involved in that program, but the engineers, are a little fussy about the fact that maybe mathematicians are not professional enough, so we don't know how to be professional, and part of what engineers learn is how to be professional. So then I guess we had the idea, well, maybe we'll start a mathematics clinic. And everybody laughed because they didn't think mathematicians were not that organized. They couldn't do it. Well, we did, by God. And so we started that. We started the clinic. So the clinic, it fits into an academic program. It's a course. It's a 2-semester course. People sign up for that course. It's usually in the senior year. It's professional in its approach, and there are handbooks and written materials for quick orientation, and all of the work is done by teams, just as you would in industry. When I was in industry, mathematicians worked in teams with engineers and physicists. That's what mathematicians do in industry. Well, that's what we did here, and that worked very well. And so we started off with one project, and it turned out to be successful. Then we had another one, and then it kept growing, and then it took off from there. So now the math clinic is a going concern. And if you want to see the things that we've done, this is an index by year of the mathematics clinic, and it's online, and it's accessible from the Harvey Mudd Math website. So if you look at this, you can go back and read just by clicking on things. Courtney worked on Chevron. Where is the Chevron? 77, 78. So Courtney worked on that. And would you say a few words about that project, Cor? Yeah, there it is.
Well, it was an interesting project. What the problem was in drilling for oil. In the process of drilling, they would encounter huge high water pockets under very high pressure. And it wasn't oil, it was water. And that would blow out the equipment entirely from the well. So what they were interested in doing was developing a model by which they could try to predict when and where these high water projects would be encountered. So we tackled that. They had a model, and what they really wanted us to do was modify the model and do some computing to see if they could use it. The first team that I had was the most successful one. And the reason it was successful is there was a mathematician. These were all Harvey Mudd undergraduates. There was a mathematician, a physicist, a chemist, and an engineer. And those four, after a little difficulty in understanding what the others were talking about, worked very well together. And that was my ideal clinic.
Whoops. I forgot to mention, when we had students working on projects in our courses, we formalized the whole process. And Courtney and I came up with a little handbook for projects that we published every year. And we spent a long time searching for good projects, which is hard to do, that were accessible to students. And so after a few years, we had quite a collection of projects. We maintained a file in our office, and we would publish an abstract of all of the projects that were done and all of the projects that were on file. And then we set up a system here for doing projects in conjunction with the course. And you're welcome to take a look at this afterwards. And we found it to be very successful as we went along. So anyway, going on from that, in connection with the clinic, you notice after a while that the same kind of solvers keep coming up time and time again. And why do you want to recreate the wheel? So our idea was maybe we should kind of get one software package, which is modular, and we could get solvers from various places and put them all together so we can access them easily. And it's very useful for the clinic. So we did that. I had 3 students at the time who were extremely talented in computers, using computers. We didn't have a computer science department, but they were very, very good in programming. And so they actually created something called MathLib, which is a collection of solvers and software tools. That it's kind of instructive. When we did that work, we were using a VAX that was running VMS. Do you see any VAXs running VMS today? We have one at Harvey Mudd. We have exactly one VAX running VMS, and we can still access MATLAB from that one VAX. When it goes, it's gone. MATLAB will be gone. It was an enormous amount of work to produce MATLAB, and just keeping it growing became impossible. And so the 3 students and I decided that to fund the further development of MATLAB, we'd have to start a company. So we did. We started a little garage company to market MATLAB. And it turned out that it was moving pretty well. Unfortunately, we had some pretty heavy competition with MATLAB and Mathematica and Maple. So we didn't get very far. So within about a year, our little company decided to shift gears, and we went into email. And that took off like a shot. The company grew, and in the year 2000, we sold the company to Sun Microsystems, which is very nice. Don't have to worry about that anymore. But anyway, that was something that we did with our students together. So that's MATLAB. Now, part of MATLAB was a lot of DE solvers. Where did we get the DE solvers? We went to NetLib. If you go to NetLib, a lot of the stuff on NetLib is from Lawrence Livermore, and it's very good software. And one of the DE solvers there was called LSODA. And LSODA was coded by Alan Heinmarsh and Linda Petzold. And Linda is now at Santa Barbara. But that is absolutely the most wonderful DE solver that we've seen. I mean, it's better than any of the DE solvers in Maple and Mathematica and all those, because it was focused on just that thing. So we liked LSODA, and so we had an idea that maybe in our DE courses, what we ought to do is to take that part of MATLAB. We take that part of MATLAB and pull it out and create something called ODE Toolkit. Now, in those days, since we were using a VAX under VMS, it had to be command line driven, which is a real pain today, but we survived with it. I mean, it was okay. We had menus there. You have to make selections from menus and type in numbers and things like that. But we did quite a bit with that, and we liked it very much, and turned out to be very successful. We used it for a long time. In fact, we used ODE Toolkit on the old VAX to do all of the graphs in our most recent textbook in DEs. So you can look at the pictures in there. I think they're pretty good. So anyway, that's ODE Toolkit came up. And then we started publishing books after that. Once we got ODE Toolkit, we decided, well, now we have to change the DE course because we have computers. And so we did all the things that you would think of now are quite commonplace. Using computers in a computer laboratory environment, working on projects, using the computers to teach differential equations. So we did all of that and wrote our book and to emphasize that. So we kept going. After that, we decided that maybe this was such a good idea that we try to share this idea with other people. So we wrote a proposal to the NSF DUE, and it was funded, and it was called CODI, Consortium for Ordinary Differential Equations Experiments. And the goal of CODI was to bring the differential equations course into the 20th century. By the year 2000. By the year 2000, yeah. And so we got that grant. CODI had, how many people did we have in phase one, Court? I think there's some 19 people involved from all over the U.S. I'll show you. Boy, this mouse is terrible. Okay. Okay, phase one of CODI Bill Boyce was in our group. Michael Branton from Stetson, Doug Campbell from West Valley College, Courtney, Wade Ellis from West Valley College, Margie Hale from Stetson University, John Hubbard from Cornell, Mike Callaher, and Mike Moody, and Arnie Ostaby, William Segman, and Beverly West from Cornell. And we also had some help from Larry Champagne. Larry was the one who designed the solvers that went into a package we called ODE Architect, which was part of Cody. And Larry Champagne used kind of a modified RK solvers, and it worked pretty well. And we produced something called ODE Architect. Some of you have seen it here, and unfortunately it only runs under Windows, so you're not going to see it very much there, but it's around. And basically, Wiley did something stupid, like publishers do. They tried to market the thing. You can't market software, for educational purposes. You give it away. They didn't believe it. They tried to market ODE Architect. It didn't work. So they finally figured that out after many years. So now they include it in the text. So if you look at our text, it contains a disk of ODE Architect.
Also Bill Boyce's text.
And Bill Boyce's text has ODE Architect in it in the text itself.
I tell Bob, we should have asked for
$1 a copy.
Well, I don't know who's using it now. I presume a lot of people are using it, but we'll never know from there. It might be amusing to I hope this works. ODE Architect has 3 pieces. It has a solver tool, it has a multimedia package, and it has a library. The library has over 100 examples that are very useful when you're teaching. It's not going to work. It can't find that file. Well, okay. Anyway, the multimedia package is kind of fun and games. And the solver tool is actually a little bit nicer, and that works, I think. The trouble with the multimedia is that Wiley designed it so that you had to have the disk in your disk drive in order to run it. And I have the disk in there, but for some reason it won't run. Anyway, okay, this is what you get with ODE Architect. The solver tool comes up like this. The editing window is on the left. The 2 graphs are over here on the right. There are about 4 different solvers that you can use here, from the Euler and some RK solvers and some of the nice solvers designed by Larry Champagne. But if you want to see an example here, it's fairly easy to use. Take something like x primed is equal to 1 minus y squared, and y primed is equal to 1 minus x squared. You put that in the editing window, you come down, you hit enter. So these graphs, the graphing screens come up. You have a choice here. There's automatic scaling, which I dislike, and then there's manual scaling. I always try to get rid of it, the automatic scaling, so I'll choose scales manually. I'll come up here and choose a scale for the x-axis, if I can get my mouse to come up here. God. I give up. I'm not going to be able to do it. Anyway, simple enough. You set the scales there, and then you point and click. You can actually you can actually solve these DEs by just pointing on the screen, clicking, and it will solve forward and backward. And it's kind of nice. You can save it if you want to. If you're teaching and you have a number of these examples that you spent a long time producing, you save them all. You can bring them all back, but please use a different mouse. Don't use the mouse where you have to slide your finger over it. That's terrible. But anyway, that's ODE Architect. And then we kind of went on from there because Courtney and I just don't know when to stop. So we produced something called the Differential Equations Laboratory Workbook, which is a collection of experiments, computer experiments. And they're all 2 pages or 4 pages long. Everything is in there that you need to illustrate all the things that come up in a DE course. So we did that. And then finally we decided, since VAX was going away, that we would try to revive ODE Toolkit, which we have done. And I think that we're going to be successful this time because we have a grant, and as part of the grant, we have a clinic project with the computer science department to actually develop ODE Toolkit. Now we have there's a rough I'm not going to show you. It's available online. The nice thing about ODE Toolkit is you can download it. Currently it's using LSOTA under Windows. Unfortunately, when you have Java and you want it to work on any platform, it's a lot of labor involved. And it doesn't work right now with Macs or under Linux, I think. It certainly works with Windows. I know that. And a few more. But that's what the clinic project is going to do, is they're going to straighten it out so that it works the way it should. And it's very easy. You can download it anywhere. It'll be online. We're going to revive the Cody newsletter.
Before we go any further,
Yeah.
Bob is a wine lover, as some of you I know. So his classic project using the architect and any of the solvers we've developed is the wine glass. There it is.
That's the autocatalytor. That's where that came from. So, yeah. So anyway, the Cody newsletter is coming back, but it's going to be online. And we're going to couple it together with ODE Toolkit so that it'll be an interactive journal article. And when you're reading the article, if there's a differential system there, you click on it, a window comes up with ODE Toolkit. You can solve, do whatever you want to do, and send a blog to somebody, just record your feelings about it, and go on from there. So that's what our aim is. That's where we're headed. And finally, the last thing that we did is, Courtney, do you want to put up the last slide on CCMS? The beginning of this year, we decided, looking at all the mathematicians in Claremont, how many mathematicians do you think are in Claremont? At these colleges? Wild guess.
40,
No.
30.
No, about 53 currently. And they're spread over 6 different departments. Some at Harvey Mudd, some at the graduate school, some at Pomona, some at CMC, and so on. So we decided that what we would do is try to bring these departments together for collaborative research projects, which is what we wanted to do. But physically you can't do it because we're all separate colleges, we're all focused on our own colleges, but you can do it virtually. So then we created something called the Claremont Center for the Mathematical Sciences. And that is, we have a website, and you can if I can kill this. I'll show you the website. Maybe I won't. Okay. Come on. I know it's in here somewhere. Anyway. I guess I didn't put it in there. Anyway, it's available online. And so that's let me have that overhead cord.
Which one?
The last one, yeah. And as far as differential equations are concerned, I'm very proud of some of the work we've done already since January. We have a proposal that went into the NSF for in the workforce program in the math sciences, and its title is Interdisciplinary Research Mentoring in the Mathematics of Medicine. It's a 5-year program for $1.8 million. We're going to hear about it next month, whether we got it. Anyway, it's a collaborative thing. We put it together. The PIs, one PI is from Harvey Mudd, the other PI is from Pomona College. Be other people involved. But this is the kind of thing that we want to do more of, having collaborative research projects. And finally, we have one more. We have in the summer of this year, there is going to be a math in industry study group and workshop in differential equations. And it's going to be here in Claremont. And there are going to be participants from Oxford, and that's the John Ockenden group from Oxford. And there are going to be participants from the Institute of Pure and Applied Math from UCLA. So that's going to be when, Ellis? Late July. So this is something, these are two things that CCMS has done already, and this is the kind of thing that we want to do more of as we go along. So I'm exhausted by all these things. So I'd be glad to answer any questions. You're welcome to come up and look at any of this material here. Thank you very much for being patient.